Hello, math fans. Finishing, maybe not, but possibly finishing this series on cutting up pancakes if you aren't sick of it. There are other pancake questions, but I'm going to finish this project. So, as I said, in 2010, 2011, 2012, I taught this honors calculus series. Each year I added to this story. We first cut up a pancake and showed that it couldn't be cut up into 9 pieces, because at the time I had a 3-year-old and I had to cut it up into pieces. I showed that I couldn't cut it up that way, but I found out that this had to be 0.26 or 26% of the way from the center to the edge. And then the year after that, I thought, well, I remember these 3D pancakes called Abelskivers, Danish pancakes, and you had to cut it at 22% from the center. And then I had, in winter 2013, a student from the year before come and say she'd like to write her senior thesis on cutting up hyperspheres. And she'd studied some articles on extending things into higher dimensions. So she came to me, which I feel terrible. I don't advise students, but I couldn't deny this because it was this project I'd spent so much time on. So first I want to apologize. I didn't put your last name, but I want to apologize to Letian that I was not more help to you. We met a handful of times. I had lots of students I was teaching. When the project finished, I always wished we could have published some of this, but I just got busier and busier with the department, and no good excuse, just wish that I could have done more with this. And since I'm not a regular researcher, I apologize. And I don't think I was the best advisor, because we just sat and I kind of solved and didn't give you good problems to work with. So anyways, she wrote up this report, and in the report did a nice long background of some other things. But we wrote this piece we went back and forth on, which was first defining what a hypersphere was. So watch my previous videos about those. At this point, we switched from using X, Y, and Z. So instead of X, we used X1. Instead of Y, we used Y1. And this is part of the challenge when you go to higher dimensions or whatever. Sorry, I meant to say X2 here. Is that it suddenly becomes harder to formalize. And if you take a course in matrices or linear algebra, you'll get better at that. But they don't call this they call this the ball means the edge and everything in the middle. A circle is actually just the edge. So if you want everything inside, you call it a 2 ball. The 3 ball is the sphere. The n ball is whatever we mean by the n-dimensional. But we're going to define the volume to be whatever you get if you extend this idea. This was the area in 2D, this was the volume in 3D. And we call this the hypervolume, or whatever you get if you extend the same idea of distance and sphere volume to higher dimension. And sometimes that's helpful in terms of, like I said, if you can have many, many variables in a problem, and it doesn't have to be mysterious. It just becomes harder to visualize. So like I said, I always think of an example where a company sells 10 objects and they want to think about how one object affects their profit. That's not unreasonable, and there's nothing sci-fi about it, even though we're talking about an 11-dimensional problem. So you could, even in that situation, define distance, like how far apart are these things in the sense of what they would be. And sometimes we can use that to find optimal solutions even when there's a many variable problem. You just lose that ability to visualize, which we like so much. Okay, so anyways, I'm just going to pick a few pieces out of the paper. So the key was, and since we'd done the case, very carefully had done the case of 2 and 3 in that project, we had better ideas. I don't think we could have done this if I hadn't done that project for a couple of years. So we said, okay, let's examine the general volume. And of course, we then looked up some research and said, Many people had studied this. But the key idea was this idea of a recurrence, which is if you just take the first two integrals and then look at the rest of it kind of looks like another one of these, but with a different starting place. So there's a lot of kind of getting scripts matched up. But just for example, this integral right here, this double integral, looks a lot like this one. In fact, if you replace this r with this, you can get something almost the same. And so through some care, you can figure out this. The reason we did 2 is because then you can do something to simplify this, which is use polar coordinates. So this is more of a discussion for Math 126 students. But if you replace this with polar coordinates and then simplify, you actually can integrate and you get this relationship, which is the volume of an n ball is the volume of an n minus 2 ball times this. And that just gives you a way that you can quickly write down a whole bunch of volumes without actually having to integrate. So that's what we did. So we said, and it turns out in doing this, you can also do the surface areas like with almost minimal effort. So we also did the surface areas. So anyways, this is pi r squared. It's the area of a circle, 2 dimensions. This is 4/3 pi r cubed. And then if you wanted the fourth one, you would say the 4 ball is 2 pi times the radius squared. And we were doing it very general here, over 4. And then you needed the 2 ball. And the 2 ball was pi r squared. So it would be 2 pi r squared over 4. And then it would be pi r squared. That's what the r of the fourth is. That's why there's a pi squared, and this simplifies to a 2. So that's how this was generated. This will be generated from this, multiplied by r squared, pi 2 over 5, and so on. What I was really surprised by, just because I had never studied these before, was that there's a relationship between surface area I'd never really thought about. And maybe you can see it if you look across here. If you multiply by n and then divide by r, you get the surface area. Now this technically is, I don't know if you still call this a surface area, it's the circumference of a circle. But an interesting thing is if you take the volume, multiply times n, and divide by r, you get surface area. I don't know, I found that kind of interesting. Had never realized that. The reason you don't realize these things is because if you're only working in 2D and 3D, you don't have very many formulas to look at. So then in the paper, we went through and talked about cutting things into thirds. I'm sure there's other interesting questions, but we were just trying to generalize the pancake question. So at that point, we got to recap. So here was the first result, my first time I did this project, where I had them cut it in thirds, written in the new notation. This represents the area of the circles from A to R. This is the 1/3 of the area of the circle. It led to this equation, which I did in a previous video, and you get this 26%. And this idea would have been really hard for me to spot, replacing A over R with T, if I hadn't done it in these previous examples. So then we said, okay, here's the volume of a sphere. The volume of a sphere from A to R. This is the key part where we're cutting it up, and we're asking where A is. Here, A was just a vertical line. Now, A is going to represent a vertical plane. But we were setting this up, and we integrated. We were able to get it down to here. We replaced this. We had this equation. That's in the previous video, and we got this 0.22. So I then was like, I don't know if we'll be able to go further, but we tried. So then we generalized, and we said we want to prove this. And then we were trying to see if we could reduce it down to something we could solve in general. So we made an observation. Which is that next thing is the same as the previous one, except the outer bounds are a little different for the volume. And then this was the key step, because otherwise we wouldn't be able to move forward. We said we actually have a formula for this. Not a formula, but we know what it looks like. What all of these have in common is they all look like some constant times r squared, and this looks like some constant times r cubed, and this looked like some constant times r to the fourth, and so on. The constant just depended on that step. So if that is indeed true, then this thing is some constant, the constant for n minus 1, times this thing raised to, what's the power? The nth power. In this case, it's n minus 1 because there's an n minus 1 there. And that's what we did. The reason there's a 2 here was because of the square root, and we said, okay, and that's really shocking because we go from having lots and lots of nested integrals to just one integral. So that was really an important piece of the observation. And then we said, okay, what are we going to do next? And we used this same trick, replacing it with x over r. And that dramatically simplified it. So we did a u substitution. And that would have been a less obvious thing to do if we hadn't done it in the other cases. We factored out all the numbers, and we got it down to just a one variable integral, which happens a lot in applications, even with many variables. And now it's just a one variable equation to solve. Now that integral can be bad, if you're talking about, depending on the n, have to do some sort of trig sub. At this point, we were sort of near the end of the research project. But the truth is, we could have spent more time thinking about the integral and thinking about what we could say precisely. But we bailed out and switched to numerical analysis from there on out. We just developed these equations. We used the constants that we knew from up here, and we were able to get a whole bunch more. And we just started solving and making a table. I never went back to it. So maybe somebody will analyze this. I mean, you could do a general trig sub, and maybe I'll spend a little bit of time thinking about it, but I have so many other projects I want to talk about, and I just wanted to give this credit. So then we did some experimentation. I'm glad that I advised on this back then, which was we did it. We said, okay, here's what we got. Let's double check that it matches. So we did. We double checked. We saw what the coefficient was, and it matched. Got us the same solution. And then we went to the next one. So this was a new one, and we plugged it in. And this is the integral I got when I just plugged it into an integrator with a 4 in here. So they did trig sub. You can see that. There's probably a lot you can say about the coefficients. Again, I didn't do that piece. And then we set it equal to this, and we got a smaller number still. Like I said, at that point, I think she needed to finish her thesis, so we just stopped. And then I wrote a little Mathematica script at that point, since we had the numbers, and I just had it generate a whole bunch of these. So we noticed a trend, which is the higher the dimension gets, the closer you have to cut to whatever we mean by the origin, for whatever that means. And actually, I went and looked, and I went to my Winter 2013 file, and I found this. I think at the time, this is a Mathematica code I wrote. I think some of the code is not here, where I actually figured out the coefficients and filled them in. And then I said, find the root of the corresponding equation you get. And it spit it out, the first few here. Those are the ones we already got. And I had it spit out a lot. So if you go to 400 dimensions, if you want to cut up the 400 dimensional hypersphere into thirds so that you can share it with your 400 dimensional friends, you would cut it at 2.15% out from the center. Now, to me, when I was studying math, initially I wasn't sort of these pure. I have a lot less interest in these pure mathematical ideas now, but hopefully that resonates with some students. I'm a much more applied person. If my family watches this video, they're going to think, all right, what a waste of time. Or they'll say, they won't call me Dr. Lovelace. They'll say, that Andy, he really is the black sheep of the family. Here is proof. So anyways, there's there's probably a lot more to be said. If this interests you, I just want to emphasize, because I think this helped me. I just want to keep emphasizing this fact that when you go into multiple dimensions, it doesn't have to be a mysterious thing. We talk about, is the universe 7-dimensional, 6-dimensional? Like, I just think about that differently now that I've done quite, enough math. I know that there are those that understand it better and can maybe visualize various things, or if they fix a variable, they can get useful visualizations out of it. And that's just not something I study. So you'll have to go to those courses. But since I've done so many business math classes, I always go back to the business example of, it's not unusual to have a situation that involves many, many variables. Okay. It is unusual to call it a volume and call it a sphere. Okay, I don't think I have anything else to add here. I hope that was of interest to you. Again, that's one of the few times that I had this project turn into something more and then turn into a research piece. So I may not have very many more video series like this. I do have several other projects I had those students do. And so each of those at some point will get a video. But that's it for now.